Okay, so then going forward, so we will now, so we have taken a DC error, multiplied, used the PI controller. So that's the first stage of ensuring that the 400 volt is available magnitude wise. But now let's get to the real deal, that is ensuring that the current is following the voltage, or the input current through the inductor is following the input voltage. Okay, so for that we take the V in, we take a reference block. So we have, let's say, a modulus function. I hope this is the one. No, not really. Mhm. Let's look at math. It's called the absolute function. Okay. Okay, so now, so we take the absolute function. So why that is the case? Because we're going to take, because yeah, we're going to take only the uh, shape of the sinusoid, let's say. So we're not really interested on whether we are dealing with the positive half cycle or the negative half cycle. So this part of the logic is only going to talk about the shape of it. So yeah, so we're going to use the absolute function. So then we will multiply. So that's how you try to have two different references. So we have already the first reference giving out you an error, and then we are trying to add into the factor of the V in here. So now we have, let's say, an error PI loop multiplied with a V reference. So what we are going to get here is just a reference which is in the shape of a sinusoid, right? So now let's parallelly try to build our current loop as well. So we take the I out, or basically, okay, here is the I out, it's here. Okay, so now I'm going to take I out. So I want to ensure that my current is also built in to this VI, to this PI loop. So here what I do is, first thing is I take the RMS value. This, I'm looking for something simpler. Yep, this should do. So this will give me a root mean square value, and then multiply, divide. I'd rather have divide here. Okay. So now the divide function. So why am I using this divide function? So so when I said we're going to have a 10 ohm, and maybe 100 microfarad capacitor. So this is going to act as a certain load, and the current is going to be in that range. So for example, 400 volts and 10 ohms, maybe around 40 amperes. But when we are trying to use the references of the V voltage, so it's somewhere around 230 volts and so on. So now it is important to have the volt ampere balance, as you can call it. So VAC in multiplied by IA in, or the IL in this case, must be equal to the V out multiplied by the I out. So that's where, so you have to do a little bit of calculation. So I'm just doing a quick one. Okay, so I'm just gonna pull out 30, 30, 30. Okay, so with this mathematics, so the IL should be 132.5 times the I out. All right, now this reference is supposed to go, and let's have, so what we are trying to do is the current reference is coming from here, the voltage reference is coming from here. So we're going to have, let's see, a divide block again, where we take in the voltage reference, then we take in the current reference, and then the next thing is, so in the previous block we said we are not worried about whether it's in the positive half or on the negative half. So that's something we have done for the voltage, but how do we handle if it is for current? Yeah. So that's where we use a switch. Okay, so we're going to use the right, so IL is here. I should have a switch, yep. This one right here. Then, so when the IL is negative, so we will multiply it with -1. So let's put a simple gain block with -1. So again, we are doing everything that we want to ensure that the logic remains the same. It's just that how we operate the switches will change. So if we are in the positive half cycle, so in the second chapter of this course, we have looked at when we are in the positive half cycle, which switches do we switch on and how the current flow happens, and similarly in the negative half cycle. So this is what we are trying to build here. So how do we know whether the voltage is positive or negative? So we take a V in, then greater than, I hope there is the block, greater than or equal to 0, yeah. So we look at this, constant. So it's this. You can also go with just a greater than, because there will be one minor data point when it is exactly at 0, and we don't want to confuse the system, so it's fine. All right, so what we are essentially saying is when the voltage is positive, so you take this, when the voltage is negative, you still multiply the current by -1 and you still take the positive values of it. All right, so now what we do is, as usual, we try to put a saturation block here because we want it to be in the limits. so which we can control it. So it's again +1 to -1. So then we try to repeat this, whatever this is called. And from here, we are again comparing it. So if you see, what we have done is this upper loop is taking in the DC references and going through the PI loop. Then we have an AC voltage reference, so we multiply it with this error. So we essentially get magnitude as well as a complete sinusoid which is coming here. And then we compare it with the current, so which is coming out on the DC side. We have a factor based on the volt ampere conservation, let's say, and then we create a reference which is again put into saturation, and then as you can expect, the next step would be a PI controller. Right, so this is my PID. We'll again go with PI. And again, at the end, we will put a saturation. This is 1 and -1. Okay, so okay, so next up, so when the error is greater than 0 and when the error is less than 0. So in the second chapter of this course, we looked at when we are trying to increase the current through the inductor, which switch should we use. So basically it's that switching which will ensure that the inductor is getting charged. So that is how we have to define now. So whatever is coming out is the final error that we're going to have. So the reference voltage and what is the current. So whatever we see here, plus or minus, is going to tell us, so if it's in the positive sides, that means the error is positive, which means the voltage is higher, but the current is not able to follow the voltage. So that is when we try to charge the inductor. So if it is in the positive half cycle, what do we do? So we switch on the switch S2. So then what we see here is the current flows through the inductor, goes through the switch S2, goes through the diode. Let's say this is D2, and then goes back. So basically nothing is entering into the load, which means the inductor is always charging. So if we have a positive error at the end of this stage, right, right here, so we're going to ensure that the switch S2 is getting pressed. So let's put that. So again, greater than or equal to, yeah, and we put a constant. Okay. Okay, so now we're ready to go. So it's going to tell us if the error is positive, this is going to be 1, if not 0. Okay, so let's define something like called as, for example, PWM high. Sorry, go to blog and then PWM high. So what we are essentially saying is PWM high, right? We want to see this. Okay, PWM high, right? Okay, so then if it is not, then we will put a not gate. Just looking for the perfect not gate. Okay, so I can use a bitwise NOT as well. Okay. Will it take it? It takes it. Okay, so similarly, I type it as PWM low. So okay, connects here. All right, so now I have to check. I have to decide how to switch on S1 and S2. So I have here the S1. Let's put it here. And S2 here. So these are going to be my actual switching pulses. All right, so what we will do here is we again have to link to this one. So if the VAC is positive, so what we said here is we have a switch again. Yeah, we have a switch here, we have a switch here. All right, so the first thing is okay. Okay, so if the voltage is greater than 0, right? So we are saying that S2 must be switched. So that means I take a PWM high, connect it here, S2 is switched, right? If not, if it is negative, it shall be PWM low. Yeah. And again, from the chapter 2, what we see is if it is negative, we are going to have PWM high switched, so it's just the opposite. So we get a PWM low and a PWM high. So that's how the logic is built. So, all right, I think we are done with our Totempole control strategy. We don't need these anymore. And yeah, so yeah, and one more thing is we need to have something called as a power GUI. So typically we would like to use it in let me save it. PFC. PC. Okay. I'll just saved. Let's have model configuration parameters. And 2 seconds is enough. So we will always have a fixed step. And yeah, ODE 5 should be good. Solver details. Like step size, we can set it 1 e power minus 6 and apply. Yeah, so here again, we cannot have it as a continuous, we need to have a discrete, and same. All right, that should be ready to go. All right then, so it's time to look at the results of our logic. So I have basically tuned some of the P and I proportional and integral constants. It's in 10 at the moment, but you can also use the Simulink tuner app. So I'm not sure, we can give it a try later on, but then yeah, so we can have a look after simulation. So right now it is simulating, and this is our scope. So what we typically see here, here the upper one is the voltage and the lower one is the current, and our target is we must see both of them are in the same phase. Okay, so here we go. Okay, that's a decent result. So, all right, so what we are seeing here is the current is trying to follow the voltage. So here you can see there are some minor blips, so which we can try and improve using, let's say, our PID controller tuning, and also sometimes, or majorly, it also depends on the values that we have. So, if we can slightly increase or decrease our inductance, we might see it getting a little bit better. Okay, so this is stable enough for me. So you see the blip position is changing right now, but more or less you see the zero crossings are matching, the peaks are matching, and so on. So, yeah. 5. The capacitor should be fine. Okay, let's try the tuner. I've never tried this before, but let's see. Okay. This doesn't seem to work at the moment. Okay, but more or less let's try and reduce the integral just to see what impact does it have. Okay, that is steady state enough. Not a lot of difference. This seems a little bit better. So when we have reduced the integral function, now let's do something else. So let's increase the proportional controller and then check it. this is steady state enough. Yeah, more or less the same. In fact, we can check it right here. So right now the switching pulses are way too much in the charging mode. These are my switching pulses. That's way too much capacitance for the DC link. Still we have the blip. I will try and correct it. Okay. Let's reduce the load current and check. This is looking better. Yep, this is looking much better. Yep. So yeah, more or less that is the way you build it. So you build a double PI loop and make sure that your electrical parameters, so it's not going to be let's say a hidden trial, it should be properly calculated. So it's a quick and dirty way to explain it. So, but you need to properly calculate. So you need to ensure when the inductor is in a continuous conducting mode, what should be your capacitance in the DC link, what is your actual load, and so on. So once you calculate the exact parameters, and then you get into this logic of operating it in the Totempole topology. So yeah, that's about it. So that's the results that we have. So we are able to ensure that the voltage and current are in phase with each other. And that is pretty much what we call it as a unity power factor, or yeah. So that's where the current is in the exact same phase as the voltage. Yeah, so that's our experiment. And yeah, that would be all. In the next video, we can have a look at how this PFC is integrated into the onboard charger.